Okay. Let us try to apply this problem, but before that I want to show you a very interesting computer code which has been used to solve the problem in the previous two examples of orthogonal structures. So, remember, in plane orthogonal structures we had two examples. The first example was a problem of this kind, okay, which had loading of this kind, and this is 3 comma ei, this is 5 comma ei, and these were the unrestrained and restrained degrees of freedom which we have marked to solve the problem. Now, I want to show you how a computer program can help you to solve this problem. We already have the solution for this, okay, which is so this value was 7.234 and this is 30.52 and this reaction 22.234 and this reaction is 63.871 in total, and this value is 13.895. Okay, this is what we got. We can solve this problem using the computer code which is being shown here. You can see here this problem solves a plane orthogonal structure using stiffness matrix method. We need to identify the number of members. Here we are given 2, okay, so because there are 2 members, that is AB and BC. Let us mark them here, AB and BC, there are 2 members. So, I have given 2 here as an input. Okay. For simplicity, since EI is constant, I have said I is and E is not varying. Okay. Length of the member is an input which is 3 meter and 5 meter, okay. 3 meter and 5 meter, you can see here, and the member numbers are 1 and 2 member number. This is member 1 and this is member 2. Okay. Now, unrestrained degrees are 2 as an input, you can see here marked in green, theta 1 and theta 2. Restrained degrees are 4, that is 3, 4, 5, 6. So, they are 4, okay. And labels of unrestrained degrees are 1 and 2, you can see here theta 1 and theta 2. So, theta 1 and theta 2, and restrained degrees are 3, 4, 5, 6. Okay. Let us see what is the global labels of member 1. Let us look at member 1. What are the local labels? Member 1 is member AB. The local labels will be 3, 1, 4 and 5. For the member BC, the labels are 1, 2, 5 and 6. So, that is what you entered here. Okay. Then let us talk about the fixed end moments. If you look at the problem, the fixed end moments has been computed like this. You already have the value in the previous lecture, please see that. Then we compute the rotational coefficients, okay. Then we get the stiffness matrix. Once we get the matrix, we print the matrix, we do the calculation, map them for different labels of each member, then we get the stiffness matrix of the entire structure, Okay. Then we try to get the unrestrained stiffness matrix alone, okay. Unrestrained stiffness matrix alone. Then we get the inverse of that, then subsequently we give the joint loads. If you look at the joint loads, we already computed this from the last lecture. Amongst these, the first two values are unrestrained joint loads. Then we use a relationship to compute the delta u, okay, delta u, which is k inverse of joint load unrestrained. Then once we get delta u, we can find the end moments of each member, member 1 and member 2. Let us see the results. You know the local stiffness matrix of the first member, if you look at the previous problem solution, you will see exactly it is same. It is for the member 2, this is for the complete structure. Now from this I cut out only these values, okay. I partition this matrix, is it not? So I get only this which I have entered here. We get the inverse of this, whereas 1 by EI is available here. In fact, in all these cases, you know, EI is constant, is it not? So here also EI is constant and so on. We get the joint load vector, then we get the unrestrained displacement, which is again 1 by EI, okay. Then we get the member end reactions, which is here. This is for the member 1, this is for the member 2, okay. Let us try to plot this. You will see for member 1, let us draw this again, okay. This is anti-clockwise 7.24 and this is clockwise because negative. So 30.52, this is upward 22.24, this is also upward 37.76. For the member 2, this for the member 1. For the member 2, you will see that this becomes 30.52, which matches with this, okay. The answer we have, which we already solved, okay, and this is 0 because it is a simply supported end for the problem. See here, the simply supported end for the problem, therefore the moment is 0 there, which we get here, okay. Then the reactions are 26.1 and 13.89, which exactly matches with this value, okay. So the sum of these two, the sum of this and this will amount to this. So the code exactly solves the same problem and the manual solution what we had matches with the results what we have in the code, okay. This is the code what we have. We are given the full code for your understanding. You can rerun the program again and try to get the results. Similarly, we can also solve the second problem which we did. If you remember, the second problem was example 2 of orthogonal structure, okay. So this is the example which we solved by hand, okay. We applied a joint load here which is 20 kilonewton meter and here 30 kilonewton meter, okay, and this was 4 meters and the height of the frame was 6 meters, right, and this is subjected to a member load of 12 kilonewton per meter and there were two more loads of 20 kilonewton and 30 kilonewton here, which are equally spaced, and there is a central load here of 50 kilonewton. This was the structure, is it not? And this member is 2I, this member had I, this member had 2I and E is constant, correct. This was the problem. Then we mark the unrestrained and restrained degrees of freedom for this problem, correct. So, the unrestrained degrees were theta 1 and theta 2, the restrained degrees were marked as theta 3, delta 4, delta 5, theta 6, delta 7, delta 8 and delta 9. This is also delta 5, this is delta 8, because axial deformations are neglected. Is it not? So, for this we have the member labels. Let us write down the labels here. It is easy to write down here. This is A, this is B, this is C and D. So, we say member BA, okay. This was my xm ym for this member. For this member this is xm and ym. For this member this is xm and this is ym, correct. So, for the member BA the labels were, I write here, okay. For the BA the labels are theta 1, theta 3 and delta 9 and delta 4. For the member BC the labels were theta 1, theta 2, delta 5 and delta 8, and for the member CD the labels were theta 2, theta 6, delta 9 and delta 7, correct. We add these values which we did in the earlier problem, please see that, okay. We have a computer coding now. There are 3 members, I am marking them with red color for our clearance. 3 members, I is varying, you can see here 2i I. So, I can say 2 1 2, fine. Member lengths in meters 6 meter, this is 4 meter, this is again 6 meter. So, 6 4 6, okay. Member numbers 1 2 and 3. How many understand degrees are there marked in green? 2, 1 and 2. So, 2 understand degrees, remaining restrained because there are total 9, is it not? So, labels are 1 and 2 for unrestrained and restrained it is 3 to 9, correct. So, let us talk about member 1, the global members 1394, you see here 1394, okay. For member 2 1258, for member 2 1258, is it not? This is 2 actually, right. This is, let us write it clearly, this is 2, right. Then 2697, 2697. So, we have it here, okay. Once we do this we get the stiffness matrix, then we apply the loads, okay. The program is continuing from here, it continues here, okay. That is how the program continues, and then we get the global end moment matrix for 3 members, member 1, member 2 and member 3. Let us write down the values which I am having here. If you compare the results what we already had shown in the previous lecture, this is my stiffness matrix for the member 1. Of course, there is a multiplier of E out, I is included in this, E is out, okay. Let us say E I and multiplier, this is E I and multiplier. You can compare these results are exactly same, and this is for the member 3 E I. This is my total stiffness matrix, okay, out of which unrestrained is this value. This is nothing but K U U. I have E I out here also, which is same as that. This is K U inverse which has 1 by E I here. This is my joint load vector which we computed. This is my delta U, okay. The delta U value is exactly same what we had. So, there is 1 by E I here, So, these are the results of end moments for first member, second member and third member. So, let us mark them separately and compare the results for our convenience. I am drawing member wise. This is the first member, this is the second member, the third member. So, this is A and B, okay. This is B and C, this is C and D, right. So, let us mark the values. So, let us A and B. So, we know A has got theta 1 here, you can see that the labels of A B, we have to transform it in the same style. The labels of A B is 1 3 9 4, okay. Comparing that 1 3 9 4, okay, that is how we have to write. So, this is going to be minus, so this is 28.4847, okay. This is anticlockwise, which is 39.7576, okay. This is minus, therefore, this is going to be 34.1212, this is 37.8788, correct. Similarly, BC, you will see this is going to be positive. So, 48.4847, okay, and this is going to be 13.5147, okay, and this value is 40 point, let us say 5, and this value is 9.5. Similarly, when you come here, this is 16.4843 and this is 59.3536 and this is negative, therefore, 11.4342 and this is 38.5658. Just for the check, the load applied here is 20 and 30, you know these two will amount to 50. Okay. Similarly, the load applied here was 50, these two amounts to 50. The load applied here was 12 for a length of 6 meters, 72. So, these two will amount to 72. Okay. So, it is very clear that the problem is examined and checked, we get the same answers as we have solved by hand using the computer method, which is stiffness matrix method. So, friends, we have given the coding, we have run the problem, we have given the results which are exactly matching with the same methodology what we solved by hand. We have one more problem which I gave you, which we only marked, which I wanted you to solve. So, the problem was example 3, okay, which I will spend few minutes in explaining the solution of this problem as well. This is the problem given, right. So, this is 6 meters and 3 I, this is 4 meters and 2 I, this is 3 meters and 2 I, this is 2 meters and 6 I, this is 3 meters and 10 I, that is the problem. Okay. We have marked the degrees of freedom, unrestrained, theta 1, theta 2, theta 3, theta 4, delta phi, delta 6, okay, and then the restraint degrees theta 8, delta 9, delta 10, theta 11, delta 12 and delta 13. So, there are 13 degrees of freedom. So, this is member nomenclature A, B, C, D, E and F. Okay. The loading were like this. Actually, this frame is subjected to 20 kilonewton here and 30 kilonewton here. That was the problem given, correct. We already said that the members BA, BA, BC, CD, DE and EF has the following labels, which is theta 1, theta 8, okay, theta 1, theta 8, then delta 5 and delta 9, is it not? Similarly, BC theta 1, theta 2, 10 and 6. Similarly, CD 2, 3, 5 and 7. Similarly, DE 3, 4, 6 and 13. EF 4, 11, 7 and 12. Okay? That is how we got. So, we wrote a program, used the same program, gave the input appropriately and developed the answers. So, this is the stiffness matrix of the first member. There is a multiplier of EI to this. The second member, multiplier of EI to this, which is exactly matching what we derived in the previous lecture, EI to this. Okay. Member 3, member 4 and member 5. These are the stiffness matrices. Then based on this, we found out the unrestrained stiffness matrix 7, because there are 7 unrestrained degrees, you can see here. So, it will be 7 by 7, 3, 7 by 7, which is going to be EI again, which is actually KUU. Okay. We inverted this matrix, okay. 1 by EI is there, we substituted joint vector and got del U, where 1 by EI is again there. Once we get this, we have obtained the end reactions of member 1, member 2, member 3, member 4 and member 5, which we can plot and give you the answers. I am plotting them here, member 1, member 2, member 3, member 4 and member 5. Okay. So, the values are very simple. I am looking for member 1. So, this is 7.98, okay, 10.9091, this is 3.148, this is 3.148. Similarly, member 2, if you look at, these are the values. So, it is going to be clockwise 7.98, you can see there is a perfect match, this is anti-clockwise and this is clockwise, is it not? So, this is going to be again clockwise 15.6556, this is minus 5.91, okay. This is plus 5.9 and so on. So, you can plot them and interpret them like this. So, friends, let us look at the summary very quickly. We have discussed about the procedure to solve non-orthogonal members. Okay. We have explained how the global end reactions can be obtained. We have also demonstrated the full computer code to solve the orthogonal structures and we said that the results what we had by hand computation are exactly matching with the computer solution, is it not? So, we have discussed about the computer methods of solving the problem. We also gave you the computer code and there is a perfect compatibility of the solution for the applied example problems. I hope you have enjoyed the lecture and I am sure you will key in this code in MATLAB and try to solve the problem once again and verify the solutions, and then you will enjoy solving more and more problems in your classrooms. Thank you very much and bye.